There are three objectives in this section. Determine intervals on which a function is concave outward or concave downward. Find any points of inflection of the graph. Apply the second derivative test to find relative extrema of a function. You have seen that locating the intervals in which a function f increases or decreases helps to describe its graph. In this section, you will see how locating the intervals f prime increases or decreases can be used to determine where the graph of f is curving upward or curving downward. The definition of concavity: let f be differentiable on an open interval I. The graph of f is concave outward on I when f prime is increasing on the interval and concave downward on interval when f prime is decreasing on the interval. The following graphical interpretation of concavity is useful. Let f be differentiable on an open interval I if the graph of f is concave outward on interval, then the graph of f lies above all of its tangent lines on I. So this is a curve of concave outward, and the f prime is increasing. So look at the tangent line. The tangent line is increasing. Let f be differentiable on an open interval I if the graph of f is concave downward on interval, then the graph of f lies below all of its tangent lines on interval. We say this curve is concave downward because the f prime is decreasing. Look at the blue line, the tangent line. They are decreasing. To find the open intervals on which the graph of a function f is concave outward or concave downward, you need to find the intervals on which f prime function is increasing or decreasing. For example, the graph of original function fx equal to 1 over 3 x cubed minus x. So look at the original graph. The original graph is concave downward on the open interval from negative infinity to 0 until 0, this point, and concave outward after 0, from 0 to infinity. This is because the curve of f prime x, we differentiate the original function to get the first derivative function, and we get x squared minus 1. This is a quadratic. It's a new function. And look at this curve of this new function. From negative infinity to 0, the slope is decreasing. So, look at the original graph. Where this part is concave downward. And for the f prime x function, from 0 to infinity, the slope at this part is increasing. While for the original curve, this part is concave outward. So this is their relationship between the increasing, decreasing, and concavity. Once again, I repeat, similarly, the graph of f is concave outward on the interval from 0 to infinity because f prime is increasing on from 0 to infinity. The next theorem shows how to use the second derivative of a function f to determine intervals on which the graph of f is concave outward or concave downward. Let f be a function whose second derivative exists on an open interval I. First, if f prime prime x greater than 0 for all x in interval, then the graph of f is concave outward on interval. If f prime prime x less than 0 for all x in interval, then the graph of f is concave downward on interval. To apply this theorem, locate the x value at which f prime prime x equal to 0, or f prime prime does not exist. Use these x values to determine test intervals. Finally, test the sign of f prime prime x in each of the test intervals. Look at this example. Determine the open intervals on which the graph of f(x), this is a rational function, is concave outward or downward. Find the second derivative of f. Now, we will write the original function into the power rule form. We differentiate the original function by using the general power rule. And we obtain first derivative function. Where the first derivative function is a rational function, so we use quotient rule to get the second derivative function. And in quotient rule, we need to use general power rule to differentiate the second function. I will simplify this function. And lastly, we have second derivative function. And we let this function equal to 0 and we solve for x. Let this function equal to 0 and we solve for x to get the critical numbers. And the critical numbers are plus minus 1. And f prime prime is defined on the entire line. You should test f prime prime in the interval from negative infinity to negative 1, from negative 1 to 1, and from 1 to infinity. Show you again the number line. So if we have two critical numbers, -1 and 1. So meaning that we have three intervals. The first interval is from -infinity to -1, and the second interval is from -1 to 1, and the third interval is from 1 to infinity. So we construct a table. The first row is interval, where we have three intervals, and the test value. Choose the test value from the respective interval, and we substitute the test value into the f'(x) function. So for the first interval, the value is positive value. So we conclude this interval is concave outward. And for the second interval, the f'(0) is negative value. So we conclude the curve on this interval is concave downward. And lastly, the f' sign is positive. So we conclude the curve is concave outward on this interval. And look at the original function. This is the original function, the curve of the original function. So for the first interval, the curve is concave outward. The curve is concave outward from -infinity to -1. And from -1 to 1, the curve is concave downward. And from -1 to infinity, the curve is concave upward. The function given in first example is continuous on the entire real number line. When there are x values at which the function is not continuous, that value should be used, along with the points at which f'(x) equal to 0 or f'(x) does not exist, to form the test intervals. If the tangent line to the graph exists at such a point where the concavity changes, that point is a point of inflection. Three types of points of inflection are shown here. So look at this curve. The points of inflection of this curve is at here, because look, you try to observe the curve. This point is between the concave outward and concave downward. And for this curve, the points of inflection is here. So this is because the above part is concave outward, and this part is concave downward. And for the third, look at this curve. This part is concave downward, and this part is concave downward. So that is why this is a point of inflection, because the concavity change. Definition of points of inflection. Let f be a function that is continuous on an open interval, and let c be a point in the interval. If the graph of f has a tangent line at this point c, fc, then this point is a point of inflection of the graph of f when the concavity of f changes from outward to downward, or from downward to outward at the point. To locate possible points of inflection, you can determine the value of x for which f'(x) equal to 0. or f prime x does not exist. This is similar to the procedure for locating relative extrema of f. If FC is a point of inflection on the graph of f, then either f prime c equal to 0 or f prime does not exist at x equal to c. Look at this example. Determine the points of inflection and discuss the concavity of the graph of fx equal to x power to the 4 minus 4x cubed. So first, write the original function. Get the first derivative function and differentiate again to get the second derivative function. And we simplify, so we get the simplest function. So we let the f prime x equal to 0. We solve for x. Then we have two critical numbers, x equal to 0 and x equal to 2. By testing the interval determined by that x value, you can conclude that they both use points of inflection. First, contract a table. Since you have two critical numbers, so we have three intervals from negative infinity to 0 and from 0 to 2, and the last interval from 2 to infinity. And we choose the test value for each interval, and we substitute the test value into the second derivative function, and we conclude. So in the first interval, the curve is concave outward because the alpha prime is positive value, and for the second interval, the f prime is negative value, so it's concave downward. And for the third interval, the f prime is positive value, so we conclude it's concave outward. And we base on this point. This is a point of 0. The x value is 0. Because from negative infinity to 0, this is an interval from negative infinity to 0, the point here. And from 0 to 2, the second interval. And the third interval is from 2 to infinity. So look at this point. 0. The coordinate is 0. Recall back the definition of points of inflection. The concavity is changes from concave outward to concave downward. So this point is the point of inflection. To get the y value, substitute 0 into the original function. This is the original function. So when x equal to 0, y equal to 0. And look at this point. This is a point. The x equal to 2. Is this point a point of inflection? Now, based on this result, the curve changes from concave downward to concave outward. So this point is points of inflection. So to get the y coordinate, we substitute into the original function, so we have negative 16. The converse of theorem 3.8 is not generally true. That is, it is possible for the second derivative to be 0 at a point that is not a point of inflection. For example, the graph of fx equal to x power to the 4. The second derivative is 0 when x equal to 0. But the point 0, 0 is not the point of inflection because the graph of f is concave outward in both intervals. Look at the derivation. The original function is x power to the 4. Get the first derivative function. We have 4x cubed. And to get the second derivative function, we differentiate the first derivative function. And we have 12x squared. And we let f prime prime x equal to 0. So we have 12x squared equal to 0 and x is equal to 0. And we substitute into the second derivative function f prime prime 0. We have substitute into here 0. We have 12 times 0 is equal to 0. Based on the theorem, the second derivative is 0 when x equal to 0. Here. But the point 0, 0, the point 0, 0, how to get the y coordinate? We substitute the x into the original function, so we get this coordinate, original function, okay? So it's not a point of inflection because the graph of f is concave outward in both intervals. Look at this interval. From negative infinity to 0, the curve is concave outward. And from 0 to infinity, the curve also is concave outward. So, the point 0, 0 is not the point of inflection. In addition to testing for concavity, the second derivative can be used to perform a simple test for relative maxima and minima. The test is based on the fact that if the graph of f is concave outward on an open interval containing c and f prime c equal to 0, then fc must be a relative minimum of f. So based on the previous statement on the previous page, the graph of a function is concave upward on an open interval containing c. This is a c point, and f prime c equal to 0. F prime c equal to 0, meaning that the slope at this point is equal to 0. So it's horizontal line. The tangent line is horizontal line. Then fc must be a relative minimum. Why we call this point is a relative minimum? Because this point is the lowest point along this curve. So, for the second statement, if the graph of a function f is concave downward, look at this, is concave downward. The curve is concave downwards. So, f prime c less than 0 on an open interval containing c. So, this is a point c. So, f prime c is negative value. So, the curve is concave downward. But f prime c equal to 0, meaning that the slope at this point is equal to 0, is horizontal line. The tangent line at this point is horizontal line. The first derivative is talking about the slope. Then fc, this point, cfc must be a relative maximum. Look at this point, it's the highest point along this curve. So now, in concave outward part, there exists a minimum point. But in concave downward, there exists a relative maximum. Let f be a function such that f prime c equal to 0, and the second derivative of f exists on an open interval containing c. If f prime c greater than 0 is positive value, so it's concave outward, then f has a relative minimum at the point cfc. If f prime c is negative value or is concave downward, then f has a relative maximum at the point cfc. If f prime c equal to 0, then the test fails. That is, f may have a relative maximum, a relative minimum, or neither. In such cases, you can use the first derivative test. Find the extrema of fx equal to negative 3x power to the 5 plus 5x cubed. Start with finding the critical numbers of f. We differentiate the original function, and we simplify. From this derivative, you can see that x equal to negative 1, 0, and 1 are the only critical numbers of f. We let the first derivative function equal to 0, and we solve for x. Then we have these three critical numbers, negative 1, 0, and 1. By finding the second derivative, we differentiate the first derivative function. We're using product rule. So we get the second derivative function, and you can apply the second derivative test. This is a second derivative test working. Construct a table. Since we have 3 points, negative 1, 0, and 1. Substitute these three values into the original function, we get the y coordinate. To study the extremal point, your table, the first row is point, is not interval. And for the second row is the sign of f prime prime x. You substitute -1, the x value, into the second derivative function. If the value is positive value, so we say this point, -1, -2, is a relative minimum. Look at the second point, 0, 0. We substitute 0 into the second derivative function. Is equal to 0. So we conclude test failed. And for the third point, we substitute the 1 into the second derivative function. We have a value is negative value. So we conclude this point, 1, 2, is relative maximum. Because the second derivative test fails at 0, 0, you can use the first derivative test and observe that f increases to the left and right of x equal to 0. So 0, 0 is neither a relative minimum nor a relative maximum, even though the graph has a horizontal tangent line at this point. Look at the first point, -1, -2. This part is concave outward. So this point is relative minimum. And look at the third point. The third point is relative maximum because it's on the curve, concave downward. And for the second point, 0, 0, is neither a relative minimum nor a relative maximum, because we substitute 0 into the f prime prime x function, the value obtained is 0. And we can say this point is a point of inflection because this point is between concave downward and concave outward. Look at the theorem of points of inflection. When the f prime prime c equal to 0, meaning that this is a point of inflection.